Hello everyone. Today we will be designing Hashset. Hashset is a very widely used data structure. You might have used it multiple times. The speciality of Hashset is that it gives us O of 1 lookups, right? So basically constant time lookups is the speciality of Hashset, and it's kind of magical how these things are implemented, how Hashset is implemented with such great precision. So let's just see for the people who do not know how hash sets work. Basically, let's say you have a value v1, and let's say this is your hash set, and you have a value v2, you have a value v3, you have a value v1, you have a value v2. These are the set of values that you want to add inside the hash set. Let's say I first added the value v1, it goes inside the hash set. I then added the value v2, it goes inside the hash set. I then added the value v3, it goes inside the hash set. Then I add the value v1. It is already inside the hash set, so nothing happens essentially. Then again the same thing with v2. It is already inside the hash set, so nothing really happens. Now, if I want to check whether v1 exists or not, it goes inside the hash set and it checks whether v1 is there. v1 is there, yes, it is there. Now, usually, if you want to search an element in an array, it most of the time takes O of n. Most of the times you do a linear search, or you can do a binary search for that matter, but it would never be constant time. This is near about constant time, so it is kind of magical that to see whether v1 exists within this set or not, it takes near about v1. And then the same thing for removal. If I want to remove v3, then I can just remove it again, O of 1, almost near about O of 1. So basically I've prepared some notes, some notes by Sitio Bhaiya. I saw that YouTube channel and I kind of understood how Hashset works internally on the low level, and that is what I'm going to be explaining here. So Hashset implementation. So this is how the Hashset looks on the lower level, right? So basically these are the values that you want to be adding. You want to be adding space A. Space A as in, these are just the variables that you want to be putting inside the hash set. This is a hash function. So every time you want to add a value, let's say v1, it goes inside the hash function. It gives out an index. It gives out a hash value, which we take as an index. We take it as an index. Whatever the hash function throws out, we take it as an index and we search here. We go to that index. We don't search, we go to that index and then we check for the number. Now what is this? This is the actual set. This is the actual set where values are being stored. So this is the actual set where values are being stored. The entire set is divided into multiple lists, multiple buckets, not list. List is a data structure in Java. My bad. These are buckets. We call them buckets. So basically what happens is, whatever, this is like a list of buckets inside the hash set. So whatever the hash function throws out for the given value, we take that as, let's say, h, that value is h. Then we go inside this at the hth index, that is such a funny word, but we're here to understand and not laugh. So that was a joke. So it goes to the hth bucket, and it checks. Now what is the bucket? The bucket can either be a linked list or it can be a binary search tree. What are we gonna study today? We are gonna be studying linked list. So for us, these buckets are linked list. So basically I want to add, remove or check for the value v1. I put it inside the hash function. The hash function spits out a value. I go to that that valueth index, that is hth index. Let's say this is the hth index, and I go there and check inside the linked list. I check inside the linked list for that particular value, and if that particular value does not exist and I want to add it, if I want to add that value and it does not exist, I add it to the front of the linked list. Okay, so this is basically an overview how the hash set works internally. Hash set, right? Hash set. So let's just read what I've written. Basically what happens here is whenever we put a value inside of a hash set, the following process takes place. First, it calculates the hash value, which essentially gives us the index of the bucket where the value is to be stored. That is what I just said. What is our hash function? Our hash function is value mod n. Value mod n. So let's say what is n? What is n? N is the number of buckets. Number of buckets. 1, 2, 3, 4, n. N is the number of buckets. So at the given index inside the bucket, we check if the value exists inside the linked list. If yes, we do not add. If no, we add it to the start of the linked list. So basically this explained us how we add inside the bucket the linked list, and for this contains, we just check and return. For remove, we remove directly as linked list handles the not found case automatically. We will go through this when we code it up. You will understand why did I write that. Now what are buckets? What are buckets? Buckets for us are basically a linked list, a data structure where we keep on adding elements. Value 1, I just go through this and I add the value 1 here. I add the value 1 there. So basically it's just a data structure which stores the given values that we are throwing at it. Now there are many buckets inside the hash set, and each bucket is accessed via an index. That's what I just said. We put the value inside the hash function, we put the value is then moduloed by load. That is the word that I used. I may be the first one to have coined that word. Anyways, we modulo that value with the number of buckets, and whatever this value, the value, we go to that particular index. I know I'm repeating stuff multiple times, but then that is exactly how this thing works, and it will both get into your brains as well, because I'm repeating it again and again and again. It would get inside my brain also, because I'm also a student. Why do I crack this? Why do I do this? Anyways, there are many buckets inside the hash set, and each bucket is accessed via an index. This I read this, right? This index depends on the value of element as the index is computed by the hash function. Okay, so it's just telling us that what we already know. Anyways, you can read it. Now, main question, how many buckets do we need? The number of buckets we needed essentially depends on the number of values that are to be stored. Now let's say I have 10 total values that I want to store inside a hash set. Then I would not create a hash set which has like 1,000 buckets, right? There's just no point, because again we're storing this inside memory, right? We're using a hash set to improve our time complexity. The space complexity will always be O of n, because hash set keeps these buckets available. So essentially the number of buckets should ideally depend on the number of values, but like you do not know how many values I'm gonna store. Like when I am coding it up, when I am coding my solution, I don't really know how many values I want to store inside the hash set. Or maybe if you're doing Leetcode, or maybe if you're doing something on the production level, you don't really know what the user is going to throw inside the hash set. Or on Leetcode, you do not know the constraints obviously in on Leetcode, but then if you define the number of buckets by yourself, then it does not really make sense, because I mean, when you want to use it custom, when you know the number of values that are to be stored, then defining the number of buckets makes sense. But when you do not really know how many values there are gonna be, then we just need a very large number, right? So, but since in most cases we do not know that, so we keep the number of buckets as a very large number, somewhere between the range of 600,000. So, like, of course, right? Because inside each bucket also there will be space for storage. So, like, if I keep 1000, then automatically, if I store even 4 values inside of the hash set, I have space for 4000 variables, 4000 values, right? 4000 unique values, I must say, because Hashset does not store duplicates. 4000 unique values. So while designing, we'll be keeping it in this range, but I'm pretty sure at scale for big companies like Google, Meta, or any Apple, any company, they have big databases. So maybe they just scale this up into more thousand, or into more 10,000, 100,000, 1 million. I don't know, but we're gonna be using a large number which is in the range of this. Now, what number? Next question is, what number do we need exactly? What number do we need exactly? We need a prime number. The basic and the most and very clear answer to this is that we need a prime number. Prime number. We need a prime number. Prime number. Prime number, though, I had learnt in my 5th grade. Why is it so useful? Our teachers used to go mad at us for not knowing the prime numbers between 1 to 20. Why is a prime number so useful? What makes a prime number unique? What makes a prime number unique? What makes a prime number unique is that it has just one factor, that is the number and 1 itself. Like, it has two factors, but 1 is a universal factor. So it has just one factor, that is the number itself. That is the number itself. It just has the number as a factor and 1. So, like, wow. Because if you see any other number, 8, it has many factors. It has 2, it has 1, of course, it has 4, right? It has 3. 8 has 3 factors. But if you take 7, 7 just has 7 and 1. It has nothing else, right? So we need a prime number. We need a prime number because any other number will have a lot of collisions, while a prime number randomizes the collision. Now, just hold this thought. I will come to the example in a moment. If all examples get stored in one bucket, then it is a very bad design. If all elements, what am I reading, man? All elements. So let's say I have v1 and v2. For both of this, the hash value spits out the same value h. Then for it makes no sense to store two consecutive numbers. Let's say not consecutive, any two numbers consecutively inside the same bucket. Let's say I have 100 numbers. Let's say I have 100 numbers which share the same hash value. Then it makes no sense to store 100 numbers inside the linked list. Then it is going to decrease our time complexity drastically. Oh, 1. It would not be near about constant. It would decrease our time. It would increase our time complexity drastically if we are storing it just inside one bucket, right? So we do not want that. That is a bad design of a hash set. So we use prime numbers. So let's come to this example. Let's say we have number of buckets as 8. I have used n as a variable for number of buckets here. Here n is the number of buckets. All the factors of this number will have some disadvantages for their multiples to be stored. Let's just read this out. 400 is a factor of 800. 400 mod 800, that is the hash function value, would give me 400. That means 400 will be stored in the bucket 400. So if my value if my value is 400 and my hash function is 400 modulo number of n, my n was 800. So what is 400 modulo 800? Let's calculate. 400 modulo 800, it is 400. So it will be stored on the 400th year. v1 will go here, v1 will go here. Now let's say 800 is also technically a factor of 800. Number itself is always a factor. 800 mod 800, 200, 0, and 800 will be stored on bucket 0. That means 400 was stored in bucket 400 and 800 will be stored in bucket 0. Right? 800 will be stored in bucket 0. Let's just come here and do it manually. So now to read the further example, now 1200 is also a multiple of 400. 1200 mod 800 gives me 400, which will also be stored at bucket 400. So again, so we have 400 and 1200 stored in the bucket 400, right? So to draw it out, if this is a bucket, this is bucket 0, this is bucket 400, right? So we were seeing our number of buckets was 800, our value 1 was 400, value 2 was 800, value 3 was 1200, value 4 was 1600, is 1600. Let's just take an example. So our hash function is equal to v mod n. N was 800, so v mod 800. So 400 mod 800 was 400, so my value was stored here. Then 800 mod 800 gives me 80, so my value was stored here. 1200 here. 1600, what is 1600 mod 800? It is again 0. 1600. So if you see, all the multiples of 400 will be either stored in 0 or stored in 400, right? Now that is not a good design, right? So if by any chance I throw so many multiples of 400 in this hash set, if I throw so many multiples of 400 inside this hash set, then that is technically a bad design, because it will only be stored here. So that linked list will be very, very long. We do not want that. The lookups will increase in time complexity. The lookups will take time because it is traversing through the linked list essentially while searching. So we do not want that. That is a bad design. So what do we do? How does prime number helps us? So let's just read it. We were here, we read this. So if many values are multiples of 400, then they'll be concentrated inside the two buckets. We just saw all the numbers will be concentrated inside the buckets 0 and 400. We do not want that. I repeat, we do not want that to happen. We want our lookups to be fast. So this is the case for all numbers except prime numbers, as they're truly randomized collision. So right now my example was n is equal to 800. If I take 700, all the multiples of 700 will be stored inside the same bucket. All the multiples of 350 will be stored inside the same bucket. We do not want that. Right? So how does prime number randomize? Now we know that the factors, oh, I cannot erase. 1 second. So the factors of a prime number are just the number itself and 1. So essentially prime numbers do not really have any multiples other than actually multiplying it by 2, 3, 4 or any other whole number, right? So like, let's say my prime number is 769. Below 769, like 800 had 400, which was a multiple. It would have 400, it would have 200, it would have 100, Like, this would keep on happening. It would just get, all these numbers would be concentrated somewhere, right? But as for 769, it has no factor, it has no factor below the number itself. The only factor would be, only multiple would be 769 into 2 into 3 into 4, like those are the only values. So if you see, for the examples that I just took, 400, 800, 1200, 1600, these are truly random, these are truly random indexes that we get. As we can clearly see that the multiple values of a number, we get truly randomized when n is a prime number. n is a prime number n is a prime number, right? So that's essentially how hash sets work. That is all the theory behind it, all the theory. I will be adding this PDF as a Google Drive link in the description, so don't worry about that. And it's just 2 pages and 3 pages with code. So let's discuss time complexity. Let us discuss time complexity. When we are using a linked list, our time complexity is n by k. Here n is the number of elements stored inside the hash set and k is the number of buckets. Let's say my k was 769 and my n is somewhere about 300, somewhere about 300. So my number 369, it's 0.4. So it is near about, this n by k as a factor is near about constant, and hence we get O of 1 lookups, we get O of 1 additions, we get O of 1, everything is O of 1. So now, and the space complexity is n plus k. So I'll explain why n by k. So each element is loaded into one of the k buckets. Any element from here goes here and is loaded either here. Aisa to, it won't happen that the value v1 would be stored somewhere outside the indices range. It would clearly not happen, right? So it will be stored somewhere inside the bucket, in some bucket. All colliding elements go inside the same linked list. So like, let's say value v1 and value v69 have the same hash function, they would be added inside the same linked list. That is also very clear, very obvious also. Then on an average, there are n by k elements in an LL. n by k elements in an LL. How did I get L by n by k? How do I know that I have n by k elements? This is very easy, very easy to understand. Let's say, what was our n? N was the number of elements inside the bucket, and k was the number of buckets. So this is a classic children chocolate problem. I have k children, these are my children, and I have n chocolates. Chocolate. I forgot the spelling. Might as well just draw a toffee. Yeah. Melody. Yeah. It has a little bit of this also. So yeah, I have n chocolates and I think k children. So if I have n chocolates, so how do I divide those n chocolates within k children? I just divide it by k, right? So let's say if I have 10 children and I have 20 chocolates, then each child will get 2 chocolates. This is classic unitary method, grade 4 mathematics. So I will remove this. I don't want my notes to have a melody, because otherwise the notes will get sweet. Ha 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 ha. Anyways, so you understood that we have n by k elements in an LL. Searching, adding, removing takes time proportional to length of n by k, and hence O of n by k. Basically, basically, whenever we traverse a linked list, it would always be proportional to the length. O of n traversal is there inside a linked list, but since our length is n by k, so we have O of n by k. But since our n by k is a very small number, hence we have near about constant time. That is how this works. People have researched this and found out that it has near about O of 1, right? So this is a very very smart way to have very less time complexity, that is near about O of 1. Now, why n plus k? Because n elements stored in k buckets, memory occupied. So essentially, if I have n values and k buckets so are already there, so these k is occupying some memory, and these n will add some memory, so it's essentially n plus k. Now, when we are using binary search tree, our time complexity decreases to O of log of n by k. 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 Log of 0.4. This is negative. Anyways, so basically it is an even smaller number is what I want to say. I will not go into the negativities of it. Let's just be positive in life. So this is not how things work in time complexity, guys. You know this. This does not really work. So this is just a representation. So a logarithm of any number would always be less than that number, right? So this is again more near to constant time than O of n by k, right? And this is also because the average time to search, add or remove elements in a balanced binary search tree is log of m, where m is n by k, and m is essentially the number of nodes. And the same thing goes for space complexity, is always O of n plus k, because we add n values and we have k buckets always ready. So basically this was our theory. I hope you all understood how a hash set works. So let's just code it up now. Firstly, we'll be creating a class bucket, because we need to initialize a lot of buckets, right? The number which we selected was 769, so we need 769 buckets. So what is a bucket? A bucket is a linked list. Let me just list of integer container. This is our bucket, public bucket. This is when we call the constructor, this public bucket will be called, and it would initialize a container as a new linked list of integer, right? So whenever this constructor is called, it will initialize the container. So like it will initialize the container. Then let's just code up functions for this. Public void insert integer val. So int index is equal to this dot container dot index of val. Basically this traverses the linked list and checks whether the val is present or not. If index is equal to -1, this dot container dot add first. So basically if the value does not exist, we add it inside that given bucket. public void remove integer val, public void remove integer val, this dot container dot remove val. Linked list handles the removal automatically and the collisions, whether the case where the number exists or does not. Public boolean contains integer val, return this dot container dot index of val is equal to -1. Essentially, if the value does not exist, then it would return -1, right? So -1 equal -1, true. So it should not really be true. So if the value is -1, -1 not equal -1, false. That means the given bucket does not contain the past value, right? So now that was our bucket, every function that we were to define in the bucket. Num of buckets is equal to 769. You can choose any prime number. Bucket equal to buckets, and this is our array of buckets, because we will be essentially having a lot of buckets, right, inside the given set. Now this dot buckets is equal to new bucket. Here we call the constructor this dot num of buckets for int I is equal to 0, I is less than num of buckets I plus plus this dot buckets at I is equal to new bucket. We call the constructor here and we initialize the bucket, we create the bucket. This we are defining what type is the array. Bucket arrays is basically we define int integer array is equal to new int size of the array. So basically we can also write it like this we also can write it like this So basically that's what I've done here, and then we did the rest of the part constructor calling there. So we initialized every bucket. Now firstly we need to create the hash function. Private int get index, int key, return key. What was the hash function? Value times number of buckets, value times number of buckets. Now we wanna add it. Int bucket index is equal to this dot get index key, and this dot buckets at bucket index dot insert key. It calls this function, it gets the value, it adds it inside the given bucket. Similarly for remove, we have the same thing. We are gonna be doing the same thing here. Int bucket index this dot remove, and here we're just gonna return dot contains key. So essentially this is our entire code. I hope. Unknown network error, my Wi-Fi is switched off. Wonderful. I hope my test cases work. my test cases work. I am submitting my code, and I have been accepted. So I hope you all understood how do we implement a hash set. Thank you. Have a great day.